today. So let us start. Here, the link that I gave you, and you can see what we plan to do. That's November 24, 11 a.m. Central, and we're going to repeat what we did last time, but we're going much deeper, and it will really work for us. So that's the plan. First of all, we'll look at the new Hello World example on IBM, and they have changed significantly and promised they will stay there, and the fact that they are requiring now to tie in with the account. I'll do all of that. And that will be their lab. And then I will show you the lab on my site, and then everything works with the explanations. That's what we're going to do. So number one, we're going to go to their Hello World right there. And we will not go like this step by step here, because we will do it in our environment anyway. But we notice one thing. First of all, they have moved here, and they announced that they are moving here like November 23rd. In other words, the move is done. And they will gradually pull all of the other materials here. Secondly, I wouldn't take anything that they say lightly. Meaning, if you don't do what they say, it will not work for you. I tried. Well, that's the hard part. So we have to do the work, and I will show you how to do it. But the good part is that you can open in Quantum Lab. So giving it away, let's click on Open on Quantum Lab. That's where it is. It says, of course, service not running. Click here and it will start. Now it is starting. And all of that is because I believe I'm logged in. Okay, we are not going to really use the server. I just wanted to point out that it's there. And for your information, you can run it. But if that is what you do, you don't learn as much. However, you can download that notebook. So what I have done is, if you go here, it says download. Let's click. And let's go to the download folder. And indeed, it is here. Of course, if you just open it, it is not useful. But if you upload it into some Python environment, that probably is useful. Hi, Gang. I'm allowing you to talk, welcoming you to talk, and giving you the link. That is what we're doing. I'm giving it to you on the chat. And here. Okay, and what I was saying is that we'll go through that. First of all, the first link is going to the source. That's where it is. You can open it in Quantum Labs. Yes, you can. And you can download. Yes, you can. But I am going to run it locally, because I think you learn more. I also think that that's much more real than you running the stuff over there. You might be able to change the code as you go, you might not. In other words, good, we have the first link, but we're going to do it here. So for your pleasure, I have put it here on GitHub, and that link is there. And I will show you all that's there, except that this is GitHub. Hi, Prabhu. And please speak. I give everybody a chance to talk. So we are going again through that, and I'm giving it again on the chat. I'm sorry for welcoming everybody, but let everybody be on the same page. So here we are. That is a hello world, but right away I will tell you, this hello world is not hello world just like see hello world, like print hello world. No, that's much more involved. And one interesting thing that the IBM decided is that they will tie you in. They will ask you to have the code. You cannot run it unless you are logged in into their server. So let us start. Open the terminal, go to the projects. So if you are going to use my notebooks, then you will probably save it to your computer, and I store it in those quantum computing labs. That's where they are. I also use the .env. I show it to you right here because I'm on the black terminal. Here you are, IBM Quantum Token. So that's what you will need, and I stored it in .env because that's the best practice to do such things. So that's one thing you need to do. Another thing that you need to do is all the setup that you're going to do, save it. Save it and save it in Conda. Like in my case, Conda activate. I call it Qiskit because that's a very natural name. That's the name of the library. There you are. Qiskit, by the way, stands for Quantum Information Science, some kind of thing. In other words, it's not just like you would call a cat, but it has some meaning. But physicists are known for jokes. So now that you have prepared your token, I'll tell you how to get it, and you have activated your environment, now you can say Jupyter Lab. And please interrupt me if anything is not clear, then right away. Open your mouth or chat and tell me what it is that it is not clear. So what that is first of all, the setup lab and then the hello world. How did I do the setup? I think I gradually created this, combining little pieces. How did I do the hello world? Well, initially I did it on my own, but then I saw that you can download right here. Now that's GitHub. Here, if you open this one, you can download it, and that's what I honestly did. So that is the downloaded from IBM. Hi, Joshua, and I'm allowing you to talk, and I'm giving you the links so that you can here, so that you can open that too. Okay, here you are. Because I suspect that when you open the Zoom, the previous links are not coming to you. But now you know where we are. We're going through the Hello World example, and this time we're doing it in the real. So first of all, you would have to set things up. So I'll show you how to set things up. I'm double clicking on that. Well, that's on GitHub. That's not interesting. No. That's the local host. And that's the setup. So, okay, you need to set up, and I chose the simplest possible setup, and that's what they say. If you just go with the default account, you still need the key, and that's right here. So let's do this. Now that's not part of anywhere, but that is part of the AI labs that I run anyway, where I learned the best practice. And the best practice is to import those .env libraries and then import the key. I showed you that key is in .env. Well, now that I've run it, you know, what we can do is click on kernel and clean all the and closing. I'm not watching any of guys coming and going because I shouldn't get distracted. But that is the setup. You see, it's on localhost, it's on my computer. It's running right here. that's running Jupyter Lab. And the first thing that I did was import this token. So let's show that. There you are. That's the real token. I'm not very much afraid that you guys will steal it because you welcome. You know, if you are going to, well, no, you could potentially rack up charges, but a hacker who wants to learn quantum computing is a praiseworthy guy. So yes, it is here, but now I'm erasing that, running it again, and I know that it's here, but it's not going to the repository. That's better this way. Now, the next thing that I'm going to do is create an account. It will not work without this, so I'm saying runtime service. Please do this, save my account. If I do this, it is saved somewhere on my local computer. I suspect it's .ibm, some kind of thing, but it doesn't matter. It's here, and if I run another notepad, it still works because I did this one. You only have to do it once. Let's do it. But note, please, that I use override equal true. So if I don't say this, let's erase it for a short time. Okay, set as default. It will tell you, no, you already have saved it. Why do you do it again? So therefore, what you do is you say overwrite is true, and now when it runs, it overwrites the previous account. Now the next thing is we have set everything up. And by the way, if you want to do it, I gave you the link to my repository. So you can clone your repository, ask any question if it doesn't work. Now we're going to authenticate to that service. In other words, in the end, we are going to run on real computers. Those real computers that a long time ago convinced me that they are real by their price. And the price, I believe, is, what's the price of quantum computing? $3 a second? $2.80 a second? Something like that. So that convinced me that they are real. And I want to authenticate with them. Right now, I'm going to run on free hardware or on emulator, but they still want me to be tied with IBM because I guess they have to change their mind. Initially, they felt like, let's educate the world in quantum computing and the world will come for us, for our implementation with open checkbooks. But they changed their mind, and now the world should come, not only will come. The next step is I have authenticated, I know who I am, so let us start the service here. What is the service? That is something that will allow me to run some kind of quantum computing. Except that I'm not going to run real hardware, I'm going to run an emulator. That's how you do it. You're saying, I want to run it on a emulator. The emulator is IBM QASM simulator, so that's not real, but it behaves as if it was. That's where I can put other emulators or simulators. And now there's a sampler. Sampler is a new interface. That means just usually get me the least busy quantum computer, which might be somewhere in Australia. But this means just pretend that you're doing this. So what I did is simply authenticated. I wanted to run a job. I ran the job and it didn't do anything, but I ran it. The result was got out of job and print the result. So it says as if quasi distributions and metadata, which all doesn't make sense. And it doesn't matter what it is. If it works, that we know that we're set up, and that is the setup. So in this setup, we have used a quantum token. How do you get it? Well, to get the quantum token, you need to log in into IBM. So for that, I need to go to my store passwords. Not that I want to show you all the passwords, but that will have the URL. Okay, so I open my database, secure database of my passwords. And search for IBM. That's where it is. And I have an account and it's called IBM ID. So I want to open this and where's the URL? Not anywhere. So okay, I'll have to guess the URL. Let's try that. Round. Probably right here. Okay, so what you do is you log in and you log in with the IBM ID. So let's really do it. I want to show you that it's real. What's my IBM ID? That's it. That's my IBM ID. There you are. Continue. Now it wants the IBM password. Okay. So that's how you get the password. And lo and behold, I'm in Educ. Okay. So then you go on and finally it shows you this is where you create your key. So that proves to you that it is real, and that shows you how you authenticate yourself so that you're ready to do the hello world. Pausing right here, giving you a chance to ask questions. No questions, everything is clear, and you can do it if you want. So, share the screen again. And what we want to do is run through hello world. This is right here. Now, the way I want to do it today is this. We will run through that, getting some reasonable understanding of what we're doing. Then we'll go back, and here we will look at the explanations. At first, we will skip the explanations. We'll limit ourselves to general understanding of what we're doing. And then we will go more into the explanation, as you see right here. Now, I'm not as brilliant to create those explanations. So when I was preparing, I used ChatGPT and I was asking it, tell me in more detail what that all means. So that leads us to the interesting question of, do I need to do it? If ChatGPT can run it and it can explain it, and bypass this pesky human. But that's another question that we will discuss perhaps in the next webinar, which is AI. For now, we will do what I promised. So let's look. That is a hello world, and it promises us after you do install and setup, which happened right here in the first one. So after you do this, it should work. And what we're going to do after we have all these libraries is, first of all, map the problem to a quantum native format. What does it mean? Is that whatever the problem is, we will express it in the QC quantum computing or Qiskit language. So map the problem to a quantum native format is sounding grand, but it really is not what we're doing. We simply create a very simple quantum circuit. The next, we will optimize it. So we will combine the different steps so that they run faster. And that, in this case, we will not do. There's nothing to optimize there. That's number 2. Number 3, we will execute what we said we will do. And number 4, we'll analyze the results. Okay, so let's go. Now here, we have all the results already prepared. That's not interesting. Let's clean it all, restart, and clear all the output. Okay, now that way, we don't know what to expect. So let's go away again. We're going to do these steps. And as you know, this is notebook. So I hold the shift key and I hit enter and it runs. That's why you don't see it. Otherwise, I could click on this run and that would also work. Now, there is a little bit of an explanation of a left order or right order. And that's about how we deal with the bits. I find that's too deep. So we can look at it later. The reason it looks so nice in Markdown is because I simply borrowed it, put it this way, from their notebook. Otherwise, it's pretty hard to imitate that kind of formatting. By the way, if you want to see how that's done, that's how it is done. So it's not magic, but it looks great. What we really want to do is this. Okay, so we will create a circuit. And again, I'm skipping most of the explanation at this point. We will create a circuit of 2 qubits and 2 classical bits. That's if we put 2, 2. If we do this, we will say 2 qubits and 2 regular bits works the same, but we don't have to, so only 1, 2. The next is apply a transform. So we built our computer quantum circuit, and then we apply the transform to qubit number 0. And that puts everything into a real, as they call, superposition state, into a state that is indeterminate from the classical point of view. And then we will apply a control X bit. Now, all this gobbledygook is explained a little later, so don't worry, just run it. Okay, now the interesting thing, I run it and it shows me now what I created. I created 2 qubits. I applied the Hadamard gate to the first one, and then I applied the CX controlled NOT to the next one. And then it gives me a warning and it says, well, you should tell me exactly what kind of plot, otherwise you get a default and a new one and so on. I tried it. So it said, do the real explanation of what you do right here. So if you do this, you get the same plot, but you don't get any warnings. And if you use the second suggestion, the new IQP style, then you get a little bit nicer looking. So for your future stuff, you might want to prefer to specify how to draw it. In other words, I bought myself a computer and that's what it looks like. And if you want to see the new looks of it, then it's this. Next step, I want to do something with this computer. So I'm preparing lots of data. Each data piece is a transform, right? We remember that what we do to our qubits is we transform them. What we transform them with is this. So it's a Pauli gate named after the famous mathematician and physicist Pauli. And it does have meaning. The ZZZI means something. So let's look at what it means. ZZ, that means that I'm creating a Pauli gate that is a tensor product of 2 Pauli matrices. So again, there's no way to avoid this, that we have vectors and we have vectors are our qubits, and we have transforms and that's operations. But that is not a simple transform. It itself is the result of two previous operations, two matrices, because every time you apply a matrix to a vector, that's an operation. Now, which ones? The Pauli Z matrix corresponds to a quantum gate that flips the phase of the state 1, but if it is 0, leaves it unchanged. In other words, it's a flip from 0 to 1. Now, if you apply this 2 times, I think it goes back. So it's an identity matrix right here. That's what this does. Later on, we'll play with it. We'll do something to it. So that's what ZZ means. 2 Z transforms. ZI. Now, I is, I believe, a unit. So it doesn't do anything, an identity matrix. So ZI is just for fun. It really is just Z, but they wrote it like ZI or IZ. First apply the identity matrix, which doesn't do anything. That's like a 1. And then apply a Z transform and so on. We will maybe look at them some more, but now let's do this. So we have multiple transforms. So there's nothing to optimize. Well, so now let's do the application of these. All right, so first of all, briefly, what it is, and then I promised we'll go back and explain this. But what it is run through the estimator, run 5,000 times, apply those transforms, and give me the results. Let's run that. Note that we are doing the real stuff. That is what wouldn't work and doesn't work, right? So what is IZ? Oh, that's because I didn't run it. So it doesn't know what it is. Now it does know what it is. And that's beautiful because errors show that you are real. So now we are running on a simulator. So we are not bothering the real hardware, but we're imitating pretty well. It waits, it thinks, and it comes back and it shows us that we are looking not only at our results, but we're also taking care of the noise. Now, our regular computers, classical computers, they don't have much noise, so you don't see that, even though occasionally a memory may misfire. But you ignore it. With the quantum computers, noise is always present, and if you go a little bit deeper than on the surface, then there are things like how do you mitigate for this noise? That is shown to us right here. We'll go at it with the explanation later on, but as I promised, so let's look at the results first. There. Now that we have calculated this, let's look at the results, and that is the observable result. Well, I think that was good to start, but now we really need the explanations. So, as I promised, what I'm going to do is going back and look at all the explanations that we've got and read them and understand what they do. Now, taking a little break, a pause, and giving you a chance to ask questions. Here. Questions. Okay, now, if there are no questions, that means, well, there is a book, Proofs and Disproofs, mathematical book, which discusses what is a proof. And it mentions that there are a few stages of understanding. One is you can repeat it. Two is, Well, maybe the first one is where you think you can repeat it, but you have not tried it. Next is when you repeat it, and then the third one is you disprove it. Okay, so we're not there yet, right? I think, guys, you are in the same stage where I'm constantly learning. It's an amazing thing, hard to understand. So always meditating on what it is. Okay, let's share the screen again, and let us now go with explanations. Here you are. So what did we do? Now, at least when you do it the second time, it is at least kind of, you already saw that. At least there's a comforting feeling that you are doing it the second time and you know what you're talking about. So this HQ, H of 0 here, that applies the Hadamard gate. To what? To qubit number 0. So we have two qubits. We remember 0 and 1 because we created them. Here you are. We created two of them. There is the 0, 1, and then there's the 1. The Hadamard gate is H with the first letter of Hadamard. And it is the one that creates a real quantum state. And that's what I call real quantum state. What they call it is superposition states. In other words, it's not just 0, it's not just 1, but it is everything in between. How do we express this everything in between? Because we're not dealing with the real quantum, so let's say photons. We express it by probabilities. It has the probability of about 0.7 of being 0, and I think about 0.7 of being 1. Now the probabilities should add up, but they have to be squared up first. So if you take 0.7 squared plus another 0.7 squared, you will get a 1. That's how we calculate probabilities. And if you don't believe me on that, right, then I will say 0.7 times, squared, okay. What is it? 0.49. And if I take the other probability, also 0.7 squared 0.49, then you do get a 1. That's one of the rules that they have to be observed, otherwise it will throw an exception. That's what Hadamard gate is. What does the transform after that? What does the following transform do? It changes those probabilities. So when you apply it to a qubit, the Hadamard transform takes the basic states and converts them to 0.7, which is such a common thing that it is usually denoted as plus or minus. That's what we've done here. So that is the operation of the program, so to say, that we're going to run, but we have not run. Right here, we're just plotting it again and again. So here we do it in, it will be fair if I, for the purpose of explanation, clear it all up again and start from the beginning. And now we have already done it many times. So we said that that's what we create. That's how we plot it, that's what it created. And we can even do it in a more presentable way, or even more presentable way. That looks so nice that I would recommend, if you show it to your friends, that's what you do. And by the way, have anyone come in? Yes. Henry, welcome. And Richard, welcome again. And now we're here, our complete team, and we're running through the first example of quantum computing. Right here, all the links are given, and that is right here. I'm putting in the chat the listing. Last time I bothered you with that, but whoever came late, they get that link. We go back. It's localhost. I'm running it on my local computer. So now, having created this, I'm creating a bunch of different transforms. What I'm going to do with them, that's later. But at least I'm preparing different transforms. I already mentioned that for the transforms to make sense, you need a real vector, a real quantum bit, qubit. And therefore, we created this qubit. We prepare all the transforms that we're going to use. And here it talks about what these transforms are. So it turns out those letters are important. It is creating a different transform. Every time I change the letters, it is creating a different transform. I call them exactly by the name of the transform. And here it explains what each transform does. But what's important is that these transforms have to be quantum transforms. You cannot just arbitrarily change the probabilities because that doesn't happen in the real world. And that all does happen in the real world. That means that I can imitate in quantum computer, I can imitate these transforms and it will not crash. All right, that is all preparation. Then we're optimizing our circuits and operators, which is absolutely not needed here because that is a trivial, very simple circuit. And now we're going to execute some of these transforms. Here they are. You remember we had 6 different transforms, and we are running our circuit with every one of these transforms. We're running it 5,000 times just because there is noise, and even the simulator imitates a little bit of noise. So when we're running these transforms, we are in fact creating a program of 6 steps that's taking our quantum bit and applying that 5,000 times. Now that runs. If I wanted to be more real, I would go here, you see backend, and here what I can do is say service least busy, meaning get me a computer that is less busy than all the other ones, and that can be anywhere in the world. But just gave me not a simulator and a real operational one. I think that what we will do is after we're done with this, we'll try to run it in real. But right now, we're creating additional options. So now I promised you the explanation. So that's how you can run using an estimator. Estimator is a new thing in the library, part of IBM Qiskit framework. And it is to create expected values of observables. What are observables? That's what happens after you apply your transforms to the to qubits. And the way you do it is like this. I got a simulator, but I promise that by the end of this experiment, we'll run the real thing. That, however, is a simulator, but a real quantum processor will work. Why will it work? Well, that's because the only way you can run this notebook is by being logged in into IBM. And I showed you how I logged in setup. So the next step is options. By creating options that will configure our execution environment. And that will include the Pesky real physical details, resilient level, optimization level, and that will control error mitigation and circuit optimization. Now, we're not solving real problems, so we just remember that That is possible, but we're not doing anything unreal. And then we talk about an estimator where we use the backend, which may be a simulator or maybe a real one. And we give it these options. So we just created the backend and created the options, and now we are using it. Now, all that is left to do is to run it. But first, we note that the observable parameter is a list of Pauli observables. And for them, you want to estimate expectation values and then do it 5,000 times. Finally, the last line is retrieving the results. That, by the way, is IBM explanation. The rest is my explanations. The queues. So when we go into the real queue, then we go into the real queue. We'll see how many people are in front of us. And usually it's a few thousand. So I don't expect we will see the result kind of in our lifetime or in the lifetime of this experiment. Okay, but let's say we do get the results. So let's keep running. These are all the explanations that we ran through. And now we want to analyze the results. And of course, that's because we didn't really run it. So let's run it again. And not skip any step as we do when explaining. It doesn't take long because we're not running the real stuff. So that's the plot. Now, these are the parameters of the plot. What we give it, we give data and values. That was the data. These were the values. And then observables goes as the X plot, X label here. And then values goes right here. So there's no magic in that. That's just a regular Python plot. By the way, what are we using for PLT? We are using matplotlib pyplot. So again, that's nothing to do with quantum computing. There's the standard things that that you use in the Python, and NumPy is your way of dealing with numbers. So you get the result, which is not all aligning on the same value just because there is noise. So let's explain that. We said that was the data, these were the values. A list of strings, that's what the data was. And values were estimated expectations from the job results. Now, we are going through a loop. In Python, that's the way you do it. You say for every case in job results, you do this. You append this complicated string to the errors. So that loop, it calculates the error bars for each observable, and it's calculated twice. A standard mean, a standard error of the means, SEM, and that is a probabilistic knowledge. So that formula assumes a normal distribution, and therefore we just plot these as we showed here. Exactly what it means is this. We plot the expectation values against the observables. We add the bars, we add the X and Y, and in the result, we visualize the result of the quantum computation, especially where we have different states, and they can, depending upon the probabilities, come up with somewhat different results. Usually you see like 1,000 results. Out of the 439 was that, and 500 whatever is left is that. That's a big subject, those errors, but we're kind of ignoring them. We just observing them. All right. I think that was great. What I will do is go back and, as promised, when we estimate this, we will take out this backend and now we put this backend and then we will again say restart and run, and we will just observe how it goes. So let's see, its execution is right in front of our eyes. It's the same preparation, same plots. Okay, where it changes is right here, because we're using a different backend. So when that gets in touch with the IBM computers, and I'm still not paying anything because somehow it works out that for simple things, even though I'm running on a real computer, I'm still not paying anything. If I would pay, that would probably be a few dollars, I expect, because that's how many seconds can that be? A couple seconds, right? A couple seconds would be $4. But you see that it's much harder. So when it comes back, it will tell me you are number so and so in the queue, but it has not come back. So let's do this. I will stop sharing. That will give you a chance to ask the questions and to express your desires for the next session. And if you don't express any desires, then I will just continue. I think that is a good format that we have now, and it will last us for a while. Until honestly I pass the IBM Qiskit certification, unless I give up. Okay, so then I'll continue just like this. By now, I think the level of explanation is quite clear. At least I'm personally satisfied with that. That's pretty much, let's do this. I'll share it again just to prove the point. And the point is that it's still hanging. It's not hanging. It's getting in touch with the real computers somewhere on IBM network all over the world. And it's getting me the least busy one. That's what's taking so much, but it does run. I did run on real hardware, and I had to wait that much. And after maybe 30 minutes, I would get a place in the queue and I would get the results. Maybe I could break it into 2 steps. Maybe first give me the back end, but no, it cannot tell me what is the job before it's submitted. And it cannot do this. In other words, I think we just have to wait. What I'll do is this. I'll keep it running, and in the end, it will give me some results. So at this point, I will save the notebook and I will demonstrate it to you next time so that you will see that it did work. It took so much time, and it was number 2000 in line. Okay, so that is the promise for the next session. Okay, so I'll stop share for now. I'll wish everybody a great weekend, and I will express the desire to see all of you next time. Okay, so everybody have a great weekend. Thank you, Victor, and thank you everybody who came.
Yeah, So, your 2 o'clock meeting, do you ever hold that?
You mean the next one, which is AI, or do you
The
mean?
next one is 1 o'clock Eastern time, and then the
Yes,
third one's 2 o'clock Eastern time.
it was. I don't know where it came to because yes, it was there. I ran it a few times,
It's
but
still there.
for many
It just has a
reasons,
it just has a broken link.
well, it should be cleaned up.
It has a broken Zoom link.
So I will ask the organizer to clean it up.
Okay.
It
I'm
should
an
be. It
engineer,
is the security one, right?
and I'll get it for you here. I just got to paste both items together.
Yeah, that will be.
Paste
So
link.
I'm not even
Well,
asking, are you interested in security or no? Because I'm not going to run it.
okay.
So yeah, we need to
Well,
fix it in the sense that it will be.
oh, it's been like that for weeks now, and ever since you
Uh,
started. And I'm an engineer. You see, I'm an electronics engineer. I like getting involved in quantum computing, though. But the thing is before we put things out production, we go through the first phase of testing. And after it's passed all the tests, then we run it for a while. It's called quality assurance. And this may be
yeah.
new for people in quantum computing, but as electronics engineers, it's the norm. And after passing off for a long time on our quality assurance, and it passes that, then we put it out into production. And then the public get to see it. And it's the same way with software. It's the same way with the simple task of scheduling online meetings. We test all the links on what we broadcast, on Meetup and on Zoom. We test all the links, make sure they work. And the thing is, and this is it's increasing more and more. And I think maybe it's the only reason it's increasing because more meetings are being held, are being scheduled. But the thing is, it is increasing, and it's like I'm wondering, does the world know how to, make sure that they're providing the proper links? And a lot of times when people try to attend a Zoom session, and they all realize the Zoom is broken, and finally the host catches on to that because someone calls them and say, "Hey, you got a broken link, man."
Well, thank you
and
very
then and
much.
then he's
So
got to
in
pass
that
off the
case,
message to everyone that is broken.
your
But
feedback worked. I already
yeah,
left a
I mean,
message for her and she will fix the link and there will
okay,
be no more of the security link.
okay, yeah, I'm excited in attending your meetings at 12 and at 1 and at 2 Eastern time.
Thank you,
So
Victor.
yeah,
We'll do it.
okay. Your 1 o'clock Eastern time is coming up next in two
Yes,
minutes.
in two
Okay,
minutes, yes.
all right. See you at that one.
Thank you. Be well.
Yep. Bye.